Okay, so hello everyone. So today we will have a class on orders and lift and LT, and it's basically a continuation of Sunana's class, which she took I think last week, a while ago. So also if you don't know yet, our IMO team came fourth overall, and like we won 4 golds and 1 silver and 1 honorable mention. It's an amazing result. Oh, is it better now? Okay, now it's working. Okay, cool. So yeah, so let's start with a problem. Mm. Okay, are you able to see this? Okay, so here's the question. Let P be a prime greater than 2. Sorry, I should have typed it before. Hello.
Hello?
Yeah. Sorry, I was having bad internet connection. Um, this is the first problem. Let P be a prime greater than 2. Prove that for any divisor D of 2 to the power P minus 1, we have D is of the form 2K times P plus 1.
Wait, your
We
screen is not
cannot see
visible.
your screen,
Can
I
you please
think.
screen share it again?
I will share the screen. I'm
Okay,
just
fine.
checking if it's
Yep,
working.
no worries.
Hmm. In the meantime, you can start trying this problem. Sorry for the inconvenience. Okay, can you see it now?
Yeah.
Okay, cool. So let P be a prime. Prove that. Okay, not even prime, any divisor. So P is a prime greater than 2. And we have to prove that any divisor of 2 to the power P minus 1 is of the form 2kP plus 1. Any ideas? Okay, nice. Can you tell, Siddhi? If you have any ideas, feel free to speak. This should be an interactive class, not just me telling the solutions. Even if you have ideas to proceed. Okay, no issues. Okay. Uh, okay, so the divisor of 2 to the power P minus 1 should always be odd, right? Because this is an odd number. So, so this is equivalent to showing that if D divides 2 to the power P minus 1, then D is congruent to 1 mod P, right? So how will you show this? Okay, let's say some prime Q divides 2 to the power P minus 1. Can you say something about Q? Do you know what are orders? At
Yes.
least the basic. Okay, let me just revise once. So, like the order of an element, let's say the order of 2 modulo a prime Q. So the order of 2 with respect to Q is the smallest number n such that 2 to the power n is congruent to 1 mod Q. This is the definition of order. say for example, our prime is 7. So if our prime is 7, then order of 2 with respect to 7 is the smallest number such that 2 to the power n is congruent to 1 mod 7. And smallest number n greater than 0, of course. So the order will be 3. This is the definition or idea of order. So what do you think the order of 2 with respect to q is? We know 2 to the power p is congruent to 1 mod q, right? Also, it's yeah. What were you saying?
I am saying that 2 to the power p is 1 mod q. So we can write by Fermat's little theorem that order of 2 by of q divides like a q minus 1.
Yes. So
And yeah,
let's say order of q with respect to 2 divides q minus 1. Yes, correct. So what do we get?
and it also divides p.
Yeah. So and the order also divides p because 2 to the power p is congruent to 1 mod q. This is you can try proving this yourself. If 2 to the power say n is congruent to 1 mod q, then the order of 2 with respect to q will divide n. And we also know order of 2 with respect to q divides p. So what do you think are the possible values of order?
So it would be either 1 or p.
Correct. Is it possible that it is 1?
For 1, p should be like no, it would be impossible because p should be like 2, I think, for 1.
Yes, correct. Because if the order is 1, then that means 2 to the power 1 is congruent to 1 mod p. But that just means that p divides 1, which won't happen. So that means the order is p. And this means p divides q minus 1. So what we got is any divisor, any prime divisor of 2 to the power p minus 1 is congruent to 1 mod p, right? Because q was any arbitrary prime which divides 2 to the power p minus 1. So if all the prime divisors are 1 mod p, that means any divisor which is just a product of some primes is also 1 mod p, right? So this implies any divisor of 2 to the power p minus 1 is congruent to 1 mod p. And to be odd implies it is of the form 2kp plus 1. And so we are done. Did you follow the proof?
Yeah.
Good. Anyone has any doubts, you can ask.
I think there should be means in that middle question, 2 to the power 1 is congruent to 1 mod q, I guess.
2 to the power 1 is congruent to 1 mod q. Yeah, sorry,
Because
my
we
bad.
take
Yeah. Got it. It was my mistake. Thanks for pointing out. So this has to be because we were looking at the order of 2 with respect to q. That's why. From this, we were able to conclude that the order has to be p, and then the order should divide q minus 1, and so p will divide q minus 1. Okay, cool. So another problem. Let p here's the question. Let P be a prime, which is of the form AB plus BC plus CA, where ABC are then show that A cube, B cube, and C cube all leave distinct residues, not P. Residue is remainder. Sorry, my internet connection is a bit bad. Can you see the screen?
Yes, we can.
Okay.
Yeah.
So yeah, here's the question. Let P be a prime of this form, where ABC are all distinct and positive. Show that A cube, B cube, C cube all leave distinct residues mod P. If you have any ideas, you can tell.
Like I have an idea that ABC cannot be like same mod 3 because like if A and B are like some same mod 3, then B should be like P plus A at least, and that would make AB plus BC plus CA greater than P.
Sorry, okay, you are saying A, B, C are distinct mod P.
Yeah.
Okay. How?
And if we say that like A and B are same mod P, A is
Okay.
B mod P,
Let A be congruent to B mod P.
then B should, if we let's say that without loss of generality, B is greater than A, then B should at least be P plus A,
Okay.
and that would make like AB plus BC plus CA greater than P.
Yes, very good. Sorry, B plus A. Okay, yeah, very good. So the first observation is A, B, C are all distinct mod P. Why? Because if A and B are equal mod P, since we know they are distinct, if B is greater than A, then B will be of the form P plus A. And so AB plus BC plus CA will be strictly greater than P, which is not possible. Very good.
I have another solution.
Okay.
We assume the contrary that A cube is congruent to B cube mod
Okay.
P.
Okay.
Then we factorize it out, A minus B into A square plus AB plus B square
Okay.
is congruent to 0.
So
Then we
yeah, go on.
then we add A minus B into AB plus BC plus CA to it.
You added.
Yeah.
Okay. So you will get A minus B into A square plus B square. Okay.
Then we
P
get
divides.
another factor, A plus B.
Okay. And we know since P is of the form AB plus BC plus CA, we can say P divides A minus B into A square plus B square plus AB, right? Is that what you are saying?
No, I was saying that we can get A plus B out from that second expression.
A plus B out. Okay, sure. So this is what A minus B into A plus B into A plus B plus C, right?
Yeah, and as P is prime, then P should divide at least one of them, but that should not be the case as P is AB plus BC plus
Yes,
CA.
yes, very good. So what this is saying is P will divide A minus B into A plus B into A plus B plus C. But we know P is also of the form AB plus BC plus CA. Now, since P is a prime, if P was dividing either of these quantities, if P was dividing this whole product, it should divide one of these quantities, right? Now we know P can't divide A minus B or A plus B or A plus B plus C because this quantity is strictly smaller than AB plus BC plus C. Right? A bigger number can't divide a smaller number. Unless, of course, the number is 0, but we know ABC are distinct. Yeah, very good. So this gives us a contradiction because P can't divide this product, and hence A cube and B cube have to be distinct mod P. Did everyone follow?
Yes, it's clear.
Yes.
Okay, very good. Nice. Okay, another problem. Prove that all the divisors okay, a better way to put it are not between so prove that D does not divide yeah, this is the question. So A greater than 0 is some positive integer, and we have to show all D between 3 and 2 to the power n plus 1 do not divide this.
I have an idea. Can I share?
Yeah, sure.
We can let that like P divides A to the power 2 to the power n plus 1.
Okay. Let P divide this.
Uh, so A to the power 2 to the power n should be minus 1 mod P.
Yes.
And like if we square both the sides, we can find like A to the power 2 to the power n plus 1
Yes.
should be 1 mod P.
Hmm.
And the order should divide like 2 to the power n plus 1, but not 2 to the power n. So the order should be 2 to the power n plus 1.
So this means the order is 2 to the power n plus 1. Yes. Okay.
And by Fermat's little theorem, we can say that 2 to the power n plus 1 must divide P minus 1.
Yes. So therefore we know 2 to the power n plus 1 must divide P minus 1.
And so P should be greater than 2 to the power n plus 1 and all the others.
And this happens for any prime p which divides this quantity. And since divisor is just a product of primes, that means that the divisor should be at least bigger than 2 to the power n plus 1. So hence proved. Did everyone follow? If you have any doubts, you can ask. Okay, I think everyone followed. Okay, do you know what are primitive roots?
We have a just a basic idea, but not much.
Okay, so let's do it for the simple case. Let P be a prime. Then G is a primitive root. If order with respect to P of G is P minus 1. So so this essentially means that G to the power 0 is G to the power 1. Or okay, I should start with this. Are all distinct. Right? So this is the definition of primitive root. Let P be a prime and G is a primitive root of P if order with respect to P of G is P minus 1. In other words, all these quantities are distinct mod P. So primitive root kind of generates all the residues mod P because all these P minus 1 quantities are distinct mod P and there are P minus 1 non-zero quantities mod P. So now a primitive root, this is the question. A primitive root is called Fibonacci. The spelling is correct. If G square is congruent to G plus 1 mod P. So let's say we have a primitive root G, which satisfies this, that G square is congruent to G plus 1 mod P. Then G minus 1 is also a primitive root mod P. Oh yeah, and a primitive root will always exist for any prime square, or a number of the form 2 times a power of prime. So okay, not prime square. Okay, primitive root always exists. For P, and I think 2 times P to the power K, where P is prime.
P should be a odd prime, I think.
Oh yeah, of course. And this is like, I think, the if and only if condition. The important thing is that it exists for a prime P. That's the most useful property. So a primitive root is called Fibonacci or fancy or whatever you want to call it. If it's a primitive root G is if it satisfies this condition as well, along with being a primitive root, then this will imply that G minus 1 is also a primitive root of P.
Like, do you have to prove that now?
Yeah,
Okay.
this is a question. I just gave the definition in case you didn't know. This is the actual question. Okay, so G minus 1 being a primitive root is equivalent to showing order of G minus 1 with respect to P is P minus 1, which is also equivalent to showing G minus 1 square up to G minus 1 to the power P minus 1 are all distinct mod P. Any ideas?
Can you give me 2 more minutes?
Yeah, sure.
I have an idea.
Okay.
I have got that G is the inverse of G minus 1 mod P.
So again, you mean
So,
this?
yes,
Yeah, because G square is congruent to G plus 1. Okay, sure.
yes. So now say G minus 1 to the power x is congruent to 1 mod P for some x.
Okay, let G minus 1.
So now G to the power negative x is also congruent to 1 mod P.
Okay.
But the if we take inverse on both sides, then g to the x is congruent to 1 mod p, as the inverse of 1 is 1. So x has to be p minus 1.
Correct. So this will mean g to the power x is also congruent to 1 mod p. And since g is a primitive root, that means x is p minus 1. And so this means the order of g minus 1 with respect to p is p minus 1. And hence g is also a primitive root of p. Very good. Okay, and we can even say more about this. If p is congruent to 3 mod 4, then g minus 2 is also a primitive root. I will just write the equation again. G square is congruent to g plus 1. Okay, I'll give you 2 minutes to think about it. Something similar should work. Okay, should I give you a hint? Or you want to try more? Okay, sure. Okay, I think I should give a hint now. So we wanted something like this, right? So we can do this g square minus 2g is congruent to minus g plus 1, right? So g into g minus 2 is congruent to this. Can you finish it now? Something similar to the first part. Let x be the order. Let x be. So what do we get? Okay, wait, this is not as straightforward as I thought. We get something like this. Now we know this is 1. Okay, so we get g to the power x is congruent to minus 1. Let's say g minus 1 is g to the power y. I mean, g will generate all powers finally, right? So let's say this happens. Then g to the power x is congruent to okay. And then this means g to the power x Straight. Okay, what else can we try? We know g into g minus 2 is congruent to minus g minus 1. Okay, what about this quantity? G to the power b minus 1 by 2 into g minus 2 to the power b minus 1 by 2 is congruent to right? And since g is a primitive root, we know this is like minus 1. This quantity we still don't know. This, since p is 3 mod 4, that means p minus 1 is 2 mod 4. And so p minus 1 by 2 has to be odd. So this is again minus 1. And this is also minus 1. Okay. So this implies this is also minus 1, right? So we know g minus 2 to the power p minus 1 by 2 is congruent to minus 1. So that means that if g minus 2 to the power x is congruent to 1 mod p, x has to divide p minus 1 and x can't divide p minus 1 by 2. So x has to be even, I think. Okay, so x is even, x divides p minus 1, x does not divide p minus 1 by 2, and we have something like this, that g to the power x into something is congruent to 1 mod p. Okay, so that just means x into y minus 1 is equal to p minus 1. Okay, any other ideas? I had not tried this problem before. I just given it. C
I
minus,
think I've got an idea.
okay.
we have derived that x is even, so g to the x must be congruent to g minus 1 to the x mod p.
G to the power x is congruent to
G
the
minus
power.
1 to the x mod p. No, no, no. I'm saying yes, yeah. That's sorry.
Wait, I didn't follow this. What has it got to do with x being even?
In the original equation, g to the x is congruent to minus 1 to the x times g minus 1 to the x mod p.
Yeah.
So g minus 1 is just inverse of x. So
Minus 1. Oh, here x was the order, right?
yes.
Yeah, and what are you doing?
So g to the 2x is congruent to 1 mod p.
Yes.
So either 2x is 2x can't be p minus 1 as it is divisible by 4.
Yes.
So p minus 1 divides 2x.
Okay. 2x. The 2x can't divide p minus 1. Because like 4 divides this and 2 divides this. Okay, 2x does not divide p minus 1.
And x is less than p.
Yes.
So that forces x to be p minus 1 over 2 if it is not p minus 1.
Wait, but 2x has to divide. Wait, how does this force x is this?
No, p minus 1 must divide 2x
Why?
because g is a primitive root.
Correct, sorry. P minus 1 divides 2x. Yes.
And because x is less than p, its maximum value is 2p minus 2.
Yes, correct.
So either x is equal to p minus 1 over 2 or x is equals to p minus 1.
Yes, correct.
So
Yeah, very good. Yeah, so should I go through the solution once? Because I just wrote it in parts. So, yeah, so the first observation is something like this holds. Now, let x be the order with respect to p of g minus 2. Then we know g power x into g minus 2 power x is this. And this quantity is 1 because it is the order. So g power x is something like this. Now let g minus 1 is g power y. We know g power 1, g power 2 up to g power p minus 1 all give distinct residues. So for some y, this should happen. So we get g power x minus 1 to the power x times g to the power xy. So g to the power x times y minus 1 is congruent to this mod p. And is congruent to 1 mod p. Okay, so we get x is even from here. Let's consider what happens for p minus 1 by 2. So this equality is settled. This equation holds, right? And we know g to the power p minus 1 by 2 is congruent to minus 1 because g is a primitive root. We don't know about g minus 2. Minus 1 to the power p minus 1 by 2 has to be minus 1 because p is congruent to 3 mod 4 and so this quantity is odd. Similarly, this has to be minus 1 because we just showed g minus 1 as a primitive root. And since this equation holds, this implies g minus 2 to the power b minus 1 by 2 is minus 1. Now, if g minus 2 to the power x is congruent to 1 mod p, then we know x must divide p minus 1 and x can't divide p minus 1 by 2. So the only possibility is if x is even. If x was odd, then this can't happen. And now since x is since x is even, from here we can say g to the power x to the power y minus 1 is congruent to 1 mod p. Okay, that is not very useful. We just know x is even. So we know g to the power 2x is also congruent to 1 mod p, because g to the power x is congruent to 1 mod p. And since g is a primitive root, we know p minus 1 should divide 2x. And
I think we could have got it from the second step.
sorry,
And I was telling about the step g minus 1 to the power p minus 1 by 2 is congruent to minus 1 mod p.
yes.
Then if we square it both sides, then g minus 2 to the power p minus 1 is congruent to 1 mod p.
Oh, that will happen by just Fermat's little theorem, right? Like any number to the power p minus 1 is congruent to 1 mod p.
Then the order I think the order should divide p minus 1, but the order should not divide p minus 1 by 2.
Yes. Yeah. So are you asking how did we get that?
Then the order must divide p minus 1, but
Yeah.
the order should not divide p minus 1 by 2.
Yes.
So the order should be p minus 1 only.
So yeah, but it can be some other even factor, right? Like wait, how can we conclude from here that it is like that? Like for example, if your p was 7, then p minus 1 is 6. And we know that 2 divides 6, but 2 does not divide 6 upon 2, that is 3. But this happens for 2, which is not equal to 6. So from here we can't conclude that x has to be b minus 1.
Oh, yes, yes, yes. I thought it wrong.
Like p minus 1 by 2 is just reducing the power of 2, kind of, right? So if x was, that's why we are saying x is even. If x was odd, this issue would not have occurred. Like if an odd number divides p minus 1, then it has to divide p minus 1 by 2, because anyway it won't divide 2. Okay, so we got g to the power 2x is congruent to 1 mod p. So p minus 1 has to divide 2x. Okay. And so we are saying x is p minus 1 by 2. Wait. This is wrong because 2x can be bigger than p minus 1, right? Yeah, we should just use this. G to the power x is congruent. Because when we are saying g to the power 2x is congruent to 1 mod p, we know x is the order, so x is less than p minus 1. But 2x is not the order, so 2x can become bigger than p minus 1.
How did we get g to the x is congruent to 1 mod p?
Alright. Okay, then we need to do more work. So we know p minus 1 divides 2x, and like we know x is less than p minus 1, but we don't know if 2x is less than p minus 1. I think this should be doable.
How did we get g to the 2x is congruent to 1 mod p?
Oh, this we got yeah. Wait, how did we get this? We know this, right? G to the power x is congruent to this. And we know no, still we can't conclude this. Okay, at least till this part, this is fine. We know x is even.
I think we got g to the 2x is congruent to 1 mod p as g as x is even, so g to the x is congruent to g minus 1 to the x mod p,
Yeah.
and g minus 1 is just the inverse of g.
G minus 1 is the inverse of G. Oh, yeah. Very good. We know G into G minus 1 is congruent to 1 because G square um, is congruent to G plus 1 mod P. We know this and we know this. And hence we know G to the power 2x is congruent to 1 mod P. Do we? Yeah. Yeah, because we know G to the power x is congruent to G to the power minus x. Okay, so G to the power 2x is congruent to 1 mod P. X we know is less than P minus 1. This we don't know. Okay, P minus 1 divides 2x. So, but we definitely know 2x is, so, okay, if x is strictly less than P minus 1, then that means 2x is also strictly less than 2 times p minus 1. And we know p minus 1 divides 2x. So that means x has to be p minus 1 by 2. Right? But we know that x is even, and here we got an odd number, so it's a contradiction. And so this implies x is equal to p minus. Yeah, I think now we are done. Did you follow this last part?
Could you please repeat?
Yeah, sure. So we know g to the power x is congruent to g minus 1 to the power x from this part. X is even, so g power x is g minus 1 to the power x, where x is the order of g minus 2. And we know g into g minus 1 is congruent to 1 mod b because g is a Fibonacci primitive group. And so this implies g to the power x is congruent to g to the power minus x because g minus 1 is just g inverse. And hence we can say g to the power 2x is congruent to 1 mod b. Now we know that since x is the order, x has to be strictly less than x has to be less than or equal to p minus 1, right? Let's assume for now that x is strictly less than p minus 1. Now we know that since p minus 1 is the order of g, that means p minus 1 has to divide 2x because g to the power 2x is common to 1 mod. Now if x is strictly less than p minus 1, that means 2x is strictly less than 2 times p minus 1. And 2x is a multiple of p minus 1. So that means 2x has to be equal to p minus 1, which is equivalent to saying x is p minus 1 by 2. But we know since p is congruent to 3 mod 4, p minus 1 by 2 is an odd number. And we had concluded here that x is an even number. So this is a contradiction. So that means x is not strictly less than p minus 1, x is equal to p minus 1. And since the order is p minus 1, that means that g minus 2 is also primitive group. Did everyone follow?
Yes.
Yeah.
Okay. Okay, I think we can do one more problem. Just a minute. Find all primes, triples of primes P, Q, R, such that we have P divides Q to the power R plus 1, Q divides R to the power P plus 1, and R divides P to the power Q plus 1. Okay, I'll just hurry a bit. So we have to find all primes PQR such that this is satisfied. Let's look at this first. let's say q to the power r, this means q to the power r is congruent to minus 1 mod p. And this also means q to the power 2r is congruent to 1 mod p. Now, what can you say about the order of q with respect to p?
It should be 2R.
Yeah, it can, yeah, it has to be 2r. So the order is something between 1, 2, r or 2r, right? Because the order has to divide 2r and r is a prime. Can the order can't be 1 clearly, otherwise q to the power r will also be congruent. Okay. So there are a few cases, I think. Like if the order was 1, then that would imply q is congruent to 1 mod p. And q to the power r is congruent to minus 1 mod p. That means 1 is congruent to minus 1 mod p. So that leaves a possibility that p is 2. So for now, let's assume all primes are greater than 2. If one of these primes is equal to 2, then the order can be 1. So we will deal with this case later on. Right now, we will assume that all these primes are greater than 2. And then in this case, the order can't be 1. The order can't be r also, because q to the power r is congruent to minus 1 and p is not equal to 2. Can the order be equal to 2? So something like q is congruent to minus 1 mod p. This can also happen, right? If this happens, then the order is 2, and since r is a odd prime, q to the power r is also congruent to minus 1 mod p. So the order can be 2 or 2r. So if the order is 2, then that just means p divides q plus 1. Otherwise, order is 2r, and that implies 2r divides p minus 1, right? So, and we'll get something like this similar for these two cases also. Yeah, can you proceed now? Which case do you want to work on first? Order is 2r.
Yeah, we can work with that. Order is 2R.
Okay, case 1. Order is 2r. So that means 2r divides p minus 1. Okay, and for the other cases, what kind of things we can get? Q divides r plus 1, or 2p divides q minus 1. And for the third case, we will get r divides p plus 1, or 2q divides r minus 1, right? And we are assuming 2r divides p minus 1. Okay. If 2r divides p minus 1, clearly r can't divide p plus 1, right? Otherwise, r has to be 2. And we are assuming r is greater than 2. So in this case, this has to be satisfied. Right? So this will also imply 2q divides r minus 1. And if 2q divides r minus 1, again q can't divide r plus 1 because q is greater than 2. So this also implies 2p divides q minus 1. Okay, and this is enough to get a contradiction, right? Because one of p, q, or r is the bigger prime, and that can't divide a smaller prime. So we get a contradiction. So this means that the only possible cases, something like this happens. P divides q plus 1, q divides r plus 1, r divides p plus 1. And PQR are greater than 2. Can this even happen? PQR greater than 2. This can't happen, right? Because if R is the biggest prime, then it can't divide a smaller prime. And P plus 1, like P is greater than 2, so P plus 1 can't be equal to R. Like the difference between P and R is at least 2, so P plus 1 is less than. So this is also not possible. So now the interesting case, P or Q or R is equal to 2. This is the interesting case. Let's say P is equal to 2 because anyway the conditions are symmetric. So it won't matter. Let P is equal to 2. Now what can we say about Q and R? 2 divides Q to the power R plus 1. That just means Q is odd and not equal to 2. So that's not very interesting. Q divides R to the power P plus, okay. Yeah, that does say something. So this means Q divides R square plus 1. And what else we have? R divides 2 to the power Q plus 1, right? And yeah, Q and R have to be odd. So will there exist such primes? Again, R square is congruent to minus 1 mod Q. So that means order with respect to Q of R has to be 4, right? It can't be anything else. And that means 4 divides q minus 1. And so q is 1 mod 4. Okay. And we know 2 to the power q is congruent to minus 1 mod r. 2 to the power 2q is congruent to 1 mod r. Now what can we say about the order? The order is something between 1, 2, q and 2q. It's clearly not q because r is not equal to 2. It can't be 1 also. It can be 2, right? Okay, if it is equal to 2, then that means 2 square is congruent to 1 mod r, and that means r is 3. So r is 3, or order is equal to 2q. So the first case is, okay, p is 2, r is 3. I think we should be able to conclude q from here. And the other case is p is 2 and order is 2q. So that means 2q divides r minus 1. Okay, we know 2q divides r minus 1 and we know q divides r square plus 1. So what can we say? Wait, that's not possible, right? Because r is congruent to 1 mod q. So that means r square plus 1 is like 2 mod q and q divides it. And we are saying that q is not equal to 2. So that's not possible. Okay, so this case also gets eliminated, right? So now the only, I think, interesting case is P is 2 and R is 3. Now, say about Q. So Q divides R Sorry. Yeah, can you see now?
Yeah.
So we almost concluded that P is 2, R is 3, and we got that Q should divide 10 and Q is not equal to 2, so Q is 5. So PQR is like 2, 3, 5, or you can do some cyclic permutation like 3, 5, 2 or 5, 2, 3. These are the only possible solutions.
Not 2, 3, 5. It should be 2, 5, 3, I think.
Oh yeah, sorry. 2, 5, 3 and the other combinations. 2, 5, 3, then 3, 2, 5, or 5, 3, 2. These are the only possibilities. Did you follow?
Yeah.
Okay, good. Okay, if anyone has any doubts, you can ask, otherwise we'll stop. Okay, I think we can stop then. So I just took a few random examples which I think helped you see how we can actually use this theory. I didn't do much theoretical stuff because you can always read it from somewhere. You can refer to modern Olympiad number theory book or any other number theory book you like for the theory. Yeah, class is over.